All right, so last time we started with this application demonstration. This is what we're doing in lecture is to implement a game that's similar to tic-tac-toe. So by showing you this, it'll hopefully help you solve this tic-tac-toe problem. And remember, don't look up code on the internet to solve the tic-tac-toe problem. You'll be defeating the purpose of the exercise. You need to think through the, um, the, the whole process of creating this program on your own. Of course, you can refer to the code that we're producing in lecture. So that's you can use that as kind of a model, if you like. But there's going to be a lot of changes that are needed to what we're looking at today. All right, so let's go back and look at that. Look at where we left off last time. Try to get reoriented. All right, here we go. So the game is called Connect 4. And well, we'll just play it. Let's see how far we got last time. So we have this grid. It's 7 columns and 6 rows. And we're playing against the computer. The player is X, the computer is O. And we need to get 4 in a row, either diagonally or vertically or horizontally. So I select a column. I'll select column 1. And it puts an X here in column 1 that's, which is where counting starts at 0. So we'll change that so that the user doesn't need to count from 0. And the computer places its move in column 0. And so we're going to continue to play column 1. And there, we should have won the game at that point, right? But we're not winning the game. So we need to do a check to see after each move by the player and each move by the computer, we need to check to see if one of them, if the player that has just made a move has won or not, or if there's a tie. I think we've already done tie, right? I think we got tie working.
Yeah.
Just to double check that. All right, this should result in a tie. I'll play column 5. The only column that the computer can play in is 5. And then and then the code will say, we'll check to see that all the cells have been filled in and therefore declare a tie. So the tie code is working. So these are all the pieces of the program that we did. We initialized the grid. We set all of the grid cells to period. And look at we're not using quotes around the period. We're using apostrophes. That's because the grid, the data type of the grid is char or character. So it doesn't store strings. It stores single characters, which are 1-byte characters, by the way. So we initialize the grid. We use the variable R because it stands for row, and the variable C because it stands for column. And then we have another function that prints the grid. Whenever we change the state of the grid, we want to display it to the user. So we call print grid for that purpose. Print grid has a nested loop, and it controls the variables R and C to change the rows and columns so that every cell in the grid is read and printed. Then there's this function. When the computer wants to make a move, it randomly chooses a column. We have to check to see whether the computer's choice is valid. If the column is already filled, the computer should not be able to move there. So we call this function canMove. So we stay in a loop, and we generate a random column number for the computer to play. And then we call this function canMove. If canMove returns false, we stay in the loop, generate another random column number. As soon as canMove returns true, we make that move, and then we check to see if the computer won the game. And after checking to see if the computer won the game, we want to check to see if there was a tie. And if the computer didn't win and there's no tie, then the user can play. And the user does the same thing. We prompt the user for input. The user enters in a column number, and then we call canMove to see if it's a valid choice. If it's not, then we stay in that loop where we ask the user to enter in a column number. And here's the function that actually does the move. A move, when you do a move, you pick a column to drop your symbol into. So you have to start at the top, or start at the bottom actually, and search upward to find an open cell to place the symbol. So the symbol will be either O or X. O for the computer, or X for the user. And of course, C is the column number. So then we need a loop here that controls the row index. So we start row 0, which is the bottom, and we check to see, is there a dot there? If there's a dot there, yeah, we can put the symbol there. If there is no dot there, then we got to go to the next row. So we're going up. We start at 0 and we go upwards. We finally find a row in column C that has a dot. That means it's an untaken cell. And then we write the symbol into it, and then we break. Now, the code that calls move will turn around and call print grid right after this. Right? So to show the user that the grid state has changed. Now here's the function that is called when it's time for the user to make a move. We call user move. Here's our loop. We sit in this loop until the user enters a valid column number. That's why inside this is an infinite loop that we break down here. If canMove returns true, then we actually call the move function and then break out of this loop and return from the function. The computer move will have a similar structure. There'll be an infinite loop. Instead of prompting the user to enter a column number, we generate our own random column number. And that's the same code. We call it canMove. If we can move, then we pass in O to the move function. Here we pass in X. We also pass in the column that's chosen. And then we break. That's if canMove returns true. Otherwise, we stay in the loop, generate another random column number. So you can see how that might work with tic-tac-toe, right? So you generate a column move. You generate a random move. And then you check to see if it's a valid move. That's if you're on the computer. If you're asking the user to make a move, we say we want the user to enter in, say, a number to represent one of the cells in the tic-tac-toe board. And then we check to see if it's a valid move. So we can pretty much use the same structure, right? And then here's a function that checks for ties. After every move, we check for tie. After every check for a win condition, well, then we call to see if it's a tie. So when the computer makes a move, we want to check to see, we don't want to check to see if it's a tie first, because the computer may have just won on the last move. So we're going to check to see if the computer wins. If the computer wins, we say the computer wins, and we terminate. If the computer doesn't win, then we check to see if it's a tie. A tie is very simple. We just check the top row of every column. the top row of every column can move needs to return false. So if can move returns true for any column in, if we can move in any column C, then it can't be a tie, we return false. So if we find a column that can move returns true, then we know it's not a tie, we return false. After checking all the columns and can move always returns false, then we'll break out of this loop and then we return true. And that's a pattern that we have. This is so common. All of those little algorithms that you've been solving, like check for prime numbers, right? You just try all the divisors. If you find a divisor, oh, you return false. It's not a prime number. See? You're in the loop. If you find one divisor, you return from the function right there and say, nope, it's not a prime number. But after trying all the prime numbers, after trying all possible divisors, if none of them are evenly divisible into the given number, then we return true. It must be prime. And then there's other examples of this this basic logic template in other contexts as well. But you see this kind of like a recurring theme. And here's the main code. The first thing we do when we start the program, this is called the entry point, program entry point. We initialize the grid, so fill the grid with dots. We're going to print the grid, so we see the grid filled with dots. And then we enter into this infinite loop. We print a new line, and then we ask the user to move. After the user gives us a column number, we move to that, we call move on that column number, and then we print the grid to show the user, the move that he or she just took. Now we want to check, right now we're checking if it's a tie, but what we want to do is check to see if the user has just won. I'm going to copy that tie code. So if the user wins, we'll print user wins. And we're done. If the user didn't win, then we'll check to see if it's a tie. If it's a tie, we print tie, we break. It's the same with the computer. After the computer moves, we print the grid so to show the user what the computer's move is. Then we check to see if the computer wins. If our computer wins function returns true, then we'll print computer wins, we'll break from the loop. Otherwise, we need to check for a tie. And that's the end of the loop. And we start all over again. So we need to implement two functions. Computer wins and user wins. I'll put it down here. So what's the data type going to be for this function? What data type does the function user wins returns? Bool, that's right. Just going to put a stub in there, okay? There we go. Well, we'll return false in the stub, so we just keep playing with that. I'll return true for the computer. It'll say the computer wins. Let's watch. Let's see if that works. See this incremental development. All right, I constructed stubs. I want to make sure it builds, and then I just want to see if it makes sense. The user won't win on its first move, but the computer will win on its very first move. Let's see if that works. See if we got things working. Enter a column 4, and the computer takes column 0, and then the computer wins. You can see down here. And the computer is always playing in the same space, right? How do we fix that? Yeah, we got to seed the random number generator. Thank you very much for that. Good. That's good. So it's srand time is 0. And we need to get some variation here. It's no fun to play the same sequence of random numbers. It's like playing Minecraft with the same seed over and over again, same world, right? Which is probably fun enough. All right, so yeah, now we're getting a different move by the computer. There we go. All right, let's figure out how do we see if the user wins. Well, I can already see this. We want to look for 4 X's in a row, horizontally, vertically, and diagonally. It'll be the same operation for computer wins. We want to look for 4 X's horizontally, vertically, diagonally. So let's use a function for that. And we'll call it wins. And we're going to look for, we want to know if the symbol, if the char symbol, that we pass in a symbol into wins, we want to know if that symbol is winning. So here, user wins, we just call wins of O. I'm sorry, X, right? X. And for computer wins, we just return wins O. And now instead of having code that's very similar to each other, basically duplication of code, we've avoided that trajectory. It's okay to actually, I was deciding, I said, well, let me just code it up there, because sometimes it's easier to be less general. So we could have just typed up the code for user wins, see, and then tested it. And then take that block of code and move it into this generic wins function, and then replace all the X's with the variable symbol. See, that might have been a better approach because it's more concrete, it's less abstract, and it's not that much longer to do. But I just had to make a decision what to do here. So I thought I could, well, it's a good time to explain this issue about code duplication. So I chose that path. Now we're going along this path. So user wins and computer wins, these 2 functions are done. So that's all they do. Now what about wins? Let's first check for a vertical win. I think that's the easiest to test. Let's check for a vertical win. I know we're going to need a loop here. And I'm just certain it's going to look like this. Because let's do, well, this isn't going to work. Let's see. Let's take a look at, oh, we didn't need that. So let's look at the board. So this is, we want to check for, did I say vertical wins or horizontal? Vertical. Let's do horizontal first, sorry. Let's do horizontal first. we're going to check for a horizontal win. So that means, look at this first dot here, okay? That's in position 0, 0. Row 0, column 0. And let's suppose there's an X there and then an X there. That's row 1, column 0. So the column is fixed. And then we're checking down through the rows. So it's row for column 0. We're going to check rows 0, 1, 2, and 3. Are they all X's? No? Okay. Then we're going to start at the next row down. Then we're going to check for column 0. We're still in column 0. We're going to check row 1, 2, 3, and 4. And then there. Are they all X's? No. All right, let's go down another column. Starting column 2. So we're going to check 2, 3, 4, and 5. Are they all X's? No. Okay, then we'll go to the next column, column 2. We'll repeat the whole process. So you can see the way I'm expressing it now, the outer loop controls what? Rows or columns? The columns, yeah. So I got this wrong. So we're going to start with
Are we doing horizontally? Can you do vertical as an example?
we'll do vertically next.
Okay.
It's one thing at a time. So the column starts at 0 and it goes to 6 and exits at 7. There we go. And then the rows start at 0 and goes down to, I said 3, right? So strictly less than 4. I got to check that now. So this is row 5. This is row 0. And this is row 5. The 6th row is row 5. And this is row 4. Row 5, if we want the check to end on row 5, then we need to start at that one there, right? So that's row 2. So I got this wrong, didn't I? This should be less than 3. Or we could have said less than or equal to 2. So here's the test. Now, if the grid of RC equals the symbol, like X in this case, we're passing in X. So you're passing in X to wins. So symbol is coming in as an X in our thinking right now as we're code stepping. If grid RC equals symbol and grid R plus 1 C is also the symbol, and grid R plus 2 is the symbol, grid R plus 3 is the symbol. Now I'm going to clean this up a little bit. Make it a little easier to read. And look, just so it lines up, I'm going to put a plus 0 here. It just makes it easier to read. I can see already I'm missing, by lining that up, I say I made a mistake. I left out the ampersand. Already I can see that. See, if you make things lined up, it's easier to catch those mistakes. All right, so let's suppose that we've got 4 symbols in a row. We're going to return true. We've got to win. That symbol is winning. You know, this is kind of unfortunate. It's like this. It's hard to read, isn't it? So how can we fix that? I think I'll fix it as follows. That didn't work. Let me do it like this. Is that better? Or is that worse? I got to get this right. There we go. I'll space it over from there. There we go. Maybe that's better. And then, so there it is. We've got the check. That should do it right there. Let's see if that works. Something's wrong there. Comparison between pointer and integer. If this, so the symbol is a char. Oh, the syntax is not right. Get the wrong language. All right, that did it. All right, let's go for 0. Oh, user wins. What's going on? How come we can't check this? What's going on there? Return wins X. Oh, we're returning true here. This should be false. Zero, 0, 0. Should say user wins. User wins. Got it. So it should also work with the computer, right? So we could try to test that, although I think it might just take too long.
I think the computer is going the same spot. The turn is going to the same spot all the time.
We're going to make the computer win. All right, 0, 1, 2, 3, 4. Ugh, the computer is so stupid. All right. This is one dumb computer. All right, so 0, 1, 2, 3. Computer wins. The last column. We did it. The game is challenging because it's hard to lose. See? That's the problem. Yeah. All right, so let's check for a vertical win now. I'll bet the code is very similar. I'll copy what we have. Vertical win. All right, let's think it out. The vertical win. So we have to go this way. So we could, 4 in a row starting in column 0, 4 in a row starting in column 1, 4 in a row starting in column 2, 4 in a row starting in column 3. So we'll have the outer loop change the columns and the inner loop change the rows, just to keep that. We don't have to do it that way, but that's how I think about it. Sorry, the outer loop changes the rows. And the inner loop changes the columns. And the columns, the last column, see 1, 2, 3, 4, right? So it's column 0, 1, 2, 3. So the last column that we want to start from is 3. So we'll change this to a 4. And the rows, we want to do all of the rows. So make that a 6. And we do if grid of R C plus 0 plus 1 plus 2 plus 3. And this will give us a vertical win. Let's see if that works. One. Oh, almost. All right, we're going to start all over. So that would be 0, 1, 2, 3. Oh, lost. Wasn't paying attention. 0. Oh, we got it. User win. So there's a vertical win on the bottom row. Now we got to do the diagonal check, and I'm just going to guess that the code lists are similar.
Like picture.
Yeah.
Isn't vertical like this?
Oh, did I get that backwards?
Yeah.
Did I really get that backwards? This is vertical and this is horizontal?
Yeah.
Wait a minute. Yeah, you're right. I get it right now?
Yeah.
Okay, thank you. All right, let's look for.
Make 2 for
Oh, yeah,
positive or negative slope.
that's right. I remember that from last time I did this. Check for
I don't know how to say that.
down sloping diagonal win. Or is it, how do you call that diagonal? When it goes,
-1 slope.
this is up sloping,
Yeah, that's 1.
down sloping?
Positive,
Yeah.
negative.
So down sloping, let's look at down sloping. That means like this,
Yeah.
this, this, and this, right? That's a win. And we could do that here. This, 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 and this, right? So if we start from here, and we go to here, and we go to here, and we go to here, we can check all those diagonals, because from this point, we hit the last column, so we can't go any further. So the columns are going to go from 0 to 3. So the columns go from 0 to 3, which is there. And the rows, you could actually start here, right? And go to 1, 0, 1, 2, and then 3. And this is the last row that we can check, row 2. Because it's this, 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 and then this one. So that's in row 3. This is a little harder to think about. So I've got sorry, row 2. The way I did it, it doesn't really matter, you know, but the way I thought it out was like this. That's the way I explained it. First, go across the columns. No, actually, yeah, first I left the row fixed, sorry. That's the way, this is the way I explained it. Set the row at 0 and then go across the column 0 to 4. Set the row to 0 and then check columns 0, 1, 2, and 3. And check the diagonal starting from those points. That's what we did first. Then we went to the next row and we checked the same columns, right? We checked this column 0 through 3 as a starting point for the diagonal. That worked. All right, so let's do that. It's going to look like this. That didn't work out. Right, so the diagonal, it's at RC, and then this right sloping, it'll be R plus 1, C plus 1, then R plus 2, C plus 2, and so on. So that's a downsloping diagonal. What about an upsloping diagonal? For upsloping, we have to start, let's see, the outer loop is a row, okay, so we fix row 0, but we want upsloping. So we can't start in row 0, we have to start down here. We have to start in row 3 here. So we start in row 3, the 4th row, and we see that we can take these, this one, and this one. We get all the way up to the top row. And so we just scan downward from row 3 down to row 5, 3, 4, and 5. And then the columns. So given these rows, we're talking about column 0. We start here. For column 0, we start here, here, and here. We consider it the upsloping diagonals. Now when we go to column 1, we start at the same row position, this row 3, and check for the 4 upsloping, the diagonal with 4 upsloping elements. And we do that all the way to column 3, the 4th column. Because we can't go any further because we'll go off the edge. So we start at 0 and we go to 4. That's the same. Now, how do we adjust this? Now we have to subtract the rows now, right? Just to be symmetric, I'll subtract 0 there. Is that right? That's it, isn't it? But the columns keep advancing. You need to think about that one. All right, let's try for a win here. 3. blocked me.
He's sneaky.
Yeah. So I need to, is it going to win? It did. I didn't even see that.
Oh yeah.
Where's it go? Oh, it won on a diagonal. Perfect.
Wow.
Perfect. Now we don't have to test it.
There we go.
That's an upsloping diagonal that the computer wins on. It looks like we got it. One little, let's do a sort of a finishing touch here. When the user, it's inconvenient to count from 0 for the user. So when the user enters in a value, what we'll do there is just increment it. Oh, so not increment it, decrement it. So, you know, if the user enters in a 1, we want it to mean 0 internally. And we can do a little check here, you know, just if we wanted to. If C is less than 0 or C is greater than, what is it, 6? Then what can we do? We want to ask the user to enter the column number again. So we're going to do, I'm just going to type in continue. See, this means resume the loop from the top, sort of go back to the top of the loop. That's what continue does. So it doesn't execute this.
Wouldn't the C less than 0 be less or equal?
You know what? I want to do it the other way. I think it's easier. If C is greater than or equal to 0, and C is less than or equal to 6, right? Then that's good. Remember, there's 7 columns, so it's 0 to 6. And we already decremented C here, so we went from user thinking to computer thinking. So if this means, oh, we could do it like this. Watch this. Make it even simpler. I have another and here. And, you know, and can move C. So there's our more complex test. So we don't even need to increase any indents there. We just have it like that. So I mean, C is valid. All right, let's try that. All right, so column 1, it's good. Column 0, oh, it doesn't take it. Column -9, it doesn't take it. There it is. I'm going to play competitively there. All right. So that's it. That's easier for the user. Now, one thing that we didn't do is if I type in, say, G for the column number, we just get an infinite loop. So we have a little extra time. So maybe what I'll do is I'll show you that, okay, what we do there. So when here at this point, when the user types in a value that cannot be converted to an integer. See, we're telling the input operator to convert user input to an integer. But if the user types in something that cannot be converted to an integer, then the input stream goes into a fail state. I think it looks like this. I'm not sure. Gotta check it. Let's see if I got it right. Let me see if that's right. Maybe that's a function call. I can't remember. I never do this, so. Ready? So I'm going to type in F. See, it says fail. So this is true. So when this is true, what we want to do is we want to clear the, I think we call clear. So I'm just doing this from old memory. We want to clear the input stream and then start again. So we'll try to do continue. Let's see if that works. That looks like a wink, right? So we don't want to wink there. All right, I type in F. No, it's not clearing. How do we clear the input stream? Do we reset? I can't remember that now. Is it reset? Let's see if that works. No, that's not it. Clear, reset, what is it? All right, we got to look it up. C++, input stream, error state, clear, I don't know, just a whole bunch of words. This is a nice resource, this C++.com site. It's a very nice resource. I hit this a lot when I have these questions. Clear sets a new value for the stream's internal error state flags. Oh, we have to pass in something. The current value of the flags is overwritten. All bits are replaced by those in state. The state is good bit, which is 0. All error flags are cleared. Let's try that. Pass in a 0. F. And I'm still in an infinite loop. I don't get it. What's going on there? So we continue. So in the case that no stream buffer is associated with the stream when the function is called, the bad bit flag is automatically set. The current state can be obtained. I don't get it. Good bit, end of file bit, fail bit, bad bit. Functions to check state. Here's an example. It's just calling clear here. I don't get it. I don't get it. There's got to be a way to do this. All right, so it's the input stream, right? So it's input base class for streams. And I don't see it. I gotta figure it out. How to clear. Well, maybe we need to flush the buffer or something like that. Let me think. I don't get it. What do we do? Anybody else doing the research on this? Maybe flushing the buffer. Ignore to the end of the line. Maybe I need to do something like that. I'm just hacking now. I'm just like guessing. So this is clear. I don't think that does anything. And then there was cin.ignore. Just gonna hack here because I'm running out of time. It's like the boss. It's like I gotta go home. My wife is calling me, but it's late, and the client is going to want to see a prototype tomorrow morning, and I'm stressed out. I gotta get this running. I got it running. I can go home now. I can't explain to the boss what I did, but I know that I stuck this in there and it worked, okay? And welcome to the real world. No, I'm not supposed to talk about the real world as a professor. I'm sort of crossing the line here. But that's the reality, folks. And so that's the end. Next time, we finished. Is there any questions? Anything? No? Okay. Yeah?
Just a question about the final.
Yeah.
Is it going to be the same class time?
Yeah. But it's 2 hours instead of an hour and 10 minutes. Or an hour and 50 minutes.
What day is it?
So what day is the final? December 9th. If someone is good at checking those things, does that agree with everybody on the date of the final?
The time of the final will be at
It's 12 in this room. And you can see here our old final exams. Remember, if you copy this code, it doesn't work because of character set issues. So if you want to run some of this code, you need to type it in, all right? So, it looks like one of the exams. We got a problem that looks like this. Implement the isLucky function. Implement isPrime. Min value, linear search. Binary search. Count occurrences. My sort.
So you're not adding anything that we learned after the second midterm?
The final covers everything except for application development.
And search, right?
So it includes search, and it includes sort.
Sort, yeah.
Our previous exam did not include sort, but the final exam does include sort. So we have a lot. How many days we have? 2 days left? Two more lectures?
We have next Monday.
So we're ahead here. We're way ahead. So we can use these 2 days to review, and that's it. We'll do a review for the next 2 days, unless there's something else you want to do, more application development, whatever. Does that sound all right? Okay.